Welcome. Welcome to the third part of this video, the video titled as Orientation and Reactivity of Benzene Ring. In the first part of the video, we have seen what is ortho-para director and what are ring activators and ring deactivators. In the second part of this video, we predicted what orientation would be if an electrophile attacks benzene ring that is attached to an electron donating group. What did I say? Let me repeat. In the second part of the video, we had predicted what the orientation of an attacking electrophile would be if an electron donating group is linked to benzene ring. Similarly, we predicted what the orientation of the incoming electrophile would be if an electron withdrawing group is attached to benzene ring. This we did solely and purely on the basis of allocation of charges. How these charges came up? For that we assumed that the electron donating group which is having a lone pair of electron would donate its electron to the pi electron system of the benzene ring. That would lead to higher electron density of the benzene ring, and we had proven that there is higher electron density at the ortho and para position. So based on that, we have determined that if an electron donating group is present, electron density would increase due to donation of electron, and not only that, the electron density would be highest at the ortho and the para position. So purely on the basis of allocation of charges or the distribution of charges, we have established a relationship between electron donating group and ortho-para orientation and ring activation. That is, if an electron donating group is present like this, then ortho-para orientation would occur and totally the electron density of the ring would increase, leading in ring activation. This is done purely on the basis of distribution of charges, which we have observed when S donates its pair of electron. Correct? In that video, that is in the second part, we have also seen that when an electron withdrawing group is present like this, as you can see here in the board, then what would happen? All electrons would be taken. The benzene's electron would be taken by this electron withdrawing group, and that would lead to deficiency of charges at ortho and para position, right? That means there is a higher electron density, relatively higher electron density at the meta position. That would lead to orientation of the electrophile at meta position. Also, there is a ring deactivation because the electrons have been withdrawn. So we were able to establish a relationship between electron withdrawing group and meta orientation here, as well as ring deactivation. So this also we have done purely on the basis of distribution of charges when an electron withdrawing group is present. We have seen how it takes charge and how the positive sign rotates around the carbon atoms of the benzene ring. So purely on the basis of how it goes around the benzene ring, we have, and how the charge goes around the benzene ring, we have established a relationship between electron donating group and ortho-para orientation and electron withdrawing group and meta orientation. Now that is all about the past. For knowing that, for understanding that much more, please do refer my video part 1 and part 2, orientation and reactivity in benzene ring, part 1 and part 2, for better understanding of that aspect. In this video, we are going to establish the same relationship. Which relationship? The same relationship, this one, right? The same relationship by another method. In that method, we are going to see the stability of carbocations. We are going to interpret orientation. We are going to predict orientation based on stability of carbocation. I'm going to explain it how we are going to establish this relationship using that method. Okay. So before coming to that method, I will just summarize what that method is all about, so you get an idea what we are going to do actually. So In that method, what we will do is we will take the benzene ring and attach. We will consider an electron donating group first, and we will allow an electrophile to attack it. Okay, we will allow it to attack at ortho position, at meta position, and at para position. Fine. So we will get three kind of carbocations. Am I right? Ortho carbocation, meta carbocation, and para carbocation. Now what we need to do is we will compare the carbocation stability. Okay, the carbocation will exhibit resonance. They will exhibit resonance on account of the charge, positive charge that develops. Correct? When the electrophile attacks, an electron pair would be taken. A positive charge would develop in the benzene ring, and that positive charge would rotate. Right? There will be resonance. So based on resonance stabilization of the carbocation, okay, we will analyze the resonance stabilization of the carbocations, respective carbocations, and then we will compare it. And what we suppose is, what we want is that ortho carbocation and para carbocation should be stable. The resonance stabilization should be great in case of ortho and para carbocation. If it is stable, what it would mean? It would mean that ortho and para carbocation will be formed much more. Their formation will be much favorable, and ortho and para product therefore will be formed as a major product. They will be formed in much more quantity. They will be formed as major product. When they will be formed as major product? Come back here. When electron donating group is present and electrophile attacks. You got the point? Yes. What we are going to prove here? We are going to allow it attack at ortho meta para position. Then we are going to compare the stability of these three carbocations. What we are supposing is that we want ortho and para carbocation to be much stable. If it is much stable, then that means these products will be formed more, right? And if such is the case, then all this happens in the presence of electron donating group. So that would establish a relationship between electron donating group and ortho and para orientation, right? Similarly, for electron withdrawing group, we will do the same. For electron withdrawing group like this, we will do the same. In that, we will compare. In that case, we expect the meta carbocation to be more stable. If such is the case, then meta product will be formed more. That would mean that electron withdrawing group is a meta director. If such is the case, we will be able to establish a relationship between electron withdrawing group and meta direction. I hope you have understood this before starting. So now we will start and prove. We will compare the three carbocations and we will prove. Okay. So let me just rub the whole thing. As I discussed, we will first go for your benzene ring here. This is the benzene ring. Let me draw this full. Yeah. Now let me attach an electron donating group. Electrophile. Allow it to attack at ortho position. Let us see the carbocation that is formed. Ortho is this. S is here with its lone pair. These two are intact, nothing happens to them. This electron pair has been given to electrophile. For this carbon there is no loss. This carbon's electron is still here, while this carbon electron has been given to the electrophile, right? It has just switched it, right, to this electrophile. So the positive sign comes here, no doubt. Now this is deficient. To negate this positive charge, this would come here, and the positive charge would come here in the next structure. So the next structure that we get, let me draw the positive charge first, fine, and the double bond here. The rest is the same. So here we go. So that is the next structure that we get, the second structure. Now to negate this positive charge, this would come here, right? When this comes here, the positive sign comes here because this carbon doesn't have any loss, correct? It just gave this electron to this position, correct? So the positive sign would come here. Let me first put the positive sign. Yes, let me rub this so that I can draw it comfortably. Fine. Now here we go. Let me draw the double bond which came now. Okay, EH. So this is the third structure. Now to negate this positively charged carbon atom, this electron pair is ready to come here. So now what we get is a structure like this. The rest is the same. When S loses its lone pair, it becomes positive. Is there any other structure that is possible? No. We can draw the resonance hybrid structure like this. Everywhere it goes except this position, positive charge is everywhere. So that is the ortho-carbocation. This is the ortho-carbocation. This carbocation would result when electrophile would attack at ortho position. If it attacks at ortho position, there will be 4 resonating structures of the carbocation. Note that point. How many resonating structures for ortho? 4. If electrophile attacks at ortho position, 4 resonating structures of the carbocation is possible. Please note this point. Now we will go for para attack. Let it attack at para position. We will go for para attack now. Let us see how many resonating structures of the carbocation are formed. Okay, let us go for para attack. So here, right, the rest is same. When it attacks here, positive charge comes here, right, because this carbon doesn't have any loss, it just gave this electron to electrophile, so the positive charge comes here. The rest is the same, no doubt. It has started. Now to negate this, this would come here and this charge would go here. So we get the second structure like this. The positive charge comes here, this would go here, this is here, rest is the same. Now you know, to negate this positive charge, this lone pair of electron would come here. We get the third structure like this. Right, and because it's lost its lone pair, it becomes positive. Now what would happen? This positive charge, it is not so stable, so this would come here back, right? When this comes here back, the positive sign comes here back. To negate this positive sign, this electron pair would come here. So we get the fourth structure like this. This electron pair comes here and the positive sign comes here, right? So any other structures possible? No. We're going to draw the resonance hybrid at para attack, a resonance hybrid of the carbocation when para attack takes place. Everywhere except that position. Now look at this. This is the resonance hybrid of the carbocation when electrophile attacks at para position. This is the structure. Now when electrophile attacks at para position of the benzene ring, when an electron, when the primary substituent that is linked to benzene ring is an electron donating substituent, how many carbocation resonating structures of the carbocation are possible? How many here? Para has 4. Note this point. So para attack would lead to carbocation that has 4 resonating structures. That has 4 resonating structures. Ortho attack leads to carbocation that has 4 resonating structure. para attack leads to carbocation that has 4 resonating structure. Now let us see the meta attack. We have to compare all, correct? As I said earlier, before we started, we have to compare all the carbocations and see which is more stable. So now let us go for meta attack and see how many resonating structures are possible. So here we go for the meta attack. This is the meta attack. Let me draw the S also here. Here are the 2 electron pair and positive sign come here. The positive sign comes here because this electron has been given to E, right? Now what would happen? What is the next structure? This pair would come here, and the next structure that we would get is like this, right? E, H, the positive sign would come here, correct? Now what would happen? What would be the third structure? Any guess? Yes, this electron pair would come here and positive sign would come here. Very good. So now this positive sign comes here and this electron pair comes here, yes, right. Any other structures possible? No. What is the resonance hybrid? We will draw that also. So everywhere except the position, meta position, right. So meta attack leads to a carbocation that has 3 resonating structures, correct? The carbocation, when meta attacks takes place, that has 3 resonating structure, correct? So ortho attack led to 4 resonating structure, para attack led to 4 resonating structure, and meta attack led to 3 resonating structures. So the theory is, the rule is, more the resonating structure, more will be the stability. More the resonating structures, more will be the stability. So here more resonating structure is at ortho and para position. Why more the resonating structure, more the stability? See, more the resonating structure, more time it would take for an electrophile to attack the benzene ring, correct? Because more area, more probability of delocalization is possible. Or if suppose if a nucleophile wants to attack a substrate, if more is the resonating structure, more probability of it getting distributed. A nucleophile would also find it difficult, right? So here an electrophile would find it difficult as number of resonating structure increase because it is delocalized at more number of places. So here we are seeing delocalization at more number of places. Delocalization of the positive charge, in fact, at more number of places. So that would lead to more resonance stabilization of ortho and para carbocation. So that means that ortho and para carbocations are more stable. So their formation will be favored. If their formation will be favored, then of course they will be formed. When they will be formed, then of course ortho and para products will be formed. Ortho and para products are formed when electron donating groups are present. When electron donating group is linked to benzene ring and electrophilic attack takes place, ortho and para products are formed. Why? Because ortho and para products are more resonance stabilized. Carbocations are resonance stabilized. Why? Because ortho and para carbocations have more resonating structures. How much? 4. While the meta carbocation has less resonating structure, therefore it is less stable. So we have established a relationship between electron donating group that is linked to benzene ring and ortho and para direction. Right? Any doubts? Hope that there is no doubt. It's very simple, correct? So that is how we are establishing a relationship between electron donating group and ortho and para direction. Now let us see the same thing. Let us see the same thing using electron withdrawing group. Electron withdrawing group. We will see that, consider electron withdrawing group that is linked to benzene ring. This is the electron withdrawing group. Allow it for electrophilic attack. Go for ortho attack. Let us see how many carbocations we are forming and what is the nature of the carbocations that are formed. Okay, so suppose it happens, then here what is happening is B is always pulling the electron, therefore A is positive and B is negative. B is electronegative atom that is linked to key atom by means of multiple bonds. So B is pulling electron, it becomes negative, and A is positive. So what would happen? A is always positive in nature, little bit, very slight positive charge exists. E comes here, draw these two undisturbed. The positive sign would come here because the electron is taken from this position and given to E plus. So the positive sign would come here, right? Now what would happen to negate this positive sign? This would come here and positive sign would come here in the next structure. Let us see. Let us draw the positive sign first and the changed electron, and baki rest is the same. Don't forget to put this positive and negative charge. That is the main thing here. Now what would happen? This electron pair would come here and positive sign would come here. So what is now happening? This is happening and positive sign has come here, and this, let me rub this, positive, negative. Where is the E? At the ortho position. These are the three resonating structures that are possible. Let me draw the resonance hybrid structure for this also. So this is the resonance hybrid structure. Everywhere there is a positive charge except this position, right? Now that is not the main thing. The thing is that it leads to three resonating structure. The attack leads to a carbocation that has three resonating structures here. 1, 2, 3. Right? These two are fine. But look at this. Positive charge on adjacent atoms. That would make it very, very energetic, because great repulsion will come if positive charge on adjacent atoms. Look at this and look at this. They are on adjacent atoms. So there will be a great repulsion in this carbocation. So this carbocation, because of this structure, it would be very unfavorable, right? The formation of such a carbocation, this is the true structure of the carbocation, right? Due to ortho attack, the formation of this carbocation is very unfavorable. Why? Because one of the resonating structure is very energetic, and that would lead to the whole carbocation being very energetic, correct, and very unstable. See? So that ortho attack is not so much favorable in this condition, right? In this situation. Now let us look at the para attack. The para attack, let us look at that too. I am going to change the arrows to here. Let us look. What would happen if para attack takes place? E, H. These two are undisturbed. Here, as I said, don't forget to put the positive and negative charge here. The positive sign comes here because the electron has been taken from here and given to E plus. Now, in the second structure, this would happen and we get a structure where again we encounter the same issues. The positive sign has come here, right? So that would make it, yeah, I don't need to tell now. You know that it is not so stable. It's not at all stable, not at all stable. Now to negate this positive charge, this electron pair would come here and positive sign would come here. Let me rub this as I have to draw. The positive sign would come here in the third structure. Let me draw the resonance hybrid also. And where we go, pardon, like this. Positive sign everywhere except this position, and here is. Now this is the correct structure, that is a combination of all these structures. This is the resonance hybrid structure. At any given time, attack at meta position will give a resonance hybrid carbocation like this. But would it be formed? That is the main thing. No. Why? Because the resonating structure, these and these are fine. 1 and 3 is fine. But look at the resonating structure 2. Positive charge is on adjacent carbon atom. That would make this structure very unstable, very energetic, and its formation would be very unfavorable. So because of this structure, the whole resonance hybrid becomes very unstable. Correct? The whole resonance hybrid would become very unstable. Therefore, formation of a para isomer is also not favorable when electron withdrawing group is present. Okay? Now let us see what would be meta attack, what carbocation it would lead us to. Let us see the meta attack also. More is to draw than to talk here, that is why I am drawing more. Now the positive sign would come here, right? Why? Because this electron has been given to E and loss is for this carbon atom, so the positive sign has come here. The second structure, in the second structure what would happen? This pair would go here and positive sign would come here. So let me draw the second structure now. Here is the electrophile. Here is our electron withdrawing group. As I said, don't forget to put this positive charge. Otherwise we would not be able to explain. Now in the third structure what would happen? Yes, you are right. I'm not going to say this time because you know it. Yes, this would come here. And positive sign, yes. Any other structure possible? No other structure is possible. Let me draw the resonance hybrid also. So everywhere except this position, that is meta position, positive sign. Please put the charges here. Yes, this is the resonance hybrid structure when attack occurs at meta position. Resonance hybrid structure of the carbocation when attack occurs at meta position, right? Now that is not the main thing. The main thing is that there are three resonating hybrid there are three resonating structures, or there are three canonical forms, right? This is okay. Yes. Are the positive charge on adjacent carbon atoms like we have seen in ortho and para? No. Is this okay? Yes. Is this okay? Yes. So in none of these structures the positive sign is on adjacent carbon atoms. So this provides us with the comparatively, relatively better and more stable resonance hybrid structure of the carbocation. Correct? And therefore the carbocation, that is meta carbocation formation, will be favored. And because meta carbocation formation will be favored, meta carbocation will be formed more. And because of that, meta product will be formed more. So meta product is formed more when electron withdrawing group is present. Therefore, electron withdrawing group is said to be meta director. Dear students, we have seen and we have proved that electron donating groups are ortho-para directors and electron withdrawing groups are meta directors. We have seen this by analyzing and comparing the stability of carbocations when ortho-para meta attack takes place, specifically when electron donating groups are present in case 1 and in case 2 when electron withdrawing groups are present. We have found out that when electron donating groups are present, then ortho-para attack is favored because of number of more resonating structures in ortho and para attack. And we have also seen that when electron withdrawing groups are present, the meta attack is favored because of unfavorable resonating structures found when ortho and para attack had taken place. Dear students, if you have liked the class and if you have understood it, please do not forget to like, share and subscribe the channel. Please share it to your colleagues and to your other students, to your friends, so that they can also learn and reshare it. Thank you very much.